Hello everyone, and welcome back for another episode of Circuit Golf. Today's circuit is a "Don't leave the freezer door open too long" alarm, whose major components fit on a 14-pin integrated circuit with some other discrete components around it. I know this circuit may look intimidating. Don't be intimidated, it's a lot easier than it looks. Some of these pieces are essentially equivalent to 555s, and they're all very similar to each other, except the first one, which is just a buffer. Let's dive right in. I'll explain it as we go, and I think you'll find it's not as difficult as you might first anticipate. This switch right here is a magnetic reed switch, and it is mounted on a door frame, and there's a magnet mounted on a door so that when the door is closed, the magnet influences the reed switch and the reed switch makes the connection. That allows this 5-volt supply voltage to flow through this 47K pull-up resistor, through the 1K, through the inductor, and into ground. So you essentially have a 47K 1K voltage divider here, which keeps the voltage on both inputs of the Schmitt trigger AND gate pretty darn close to ground. When the door opens, the switch also opens because the magnet moves away, and there's nothing to shunt the current to ground, so the 47K resistor rather quickly charges the 100 nanofarad capacitor, and the output of this buffer goes high. Now you may ask, why did you bother with this sort of crazy RLC filter here? That 1000 microhenry, aka 1 millihenry inductor is going to be fairly expensive. Are you sure you need it? Well, no, I'm not sure. However, I do anticipate that these lines that lead to the switch and the door probably are going to be pretty long. I'm guessing that someone is going to use unshielded cable, probably going to be running them near fluorescent lights, and likely they'll be running nearby some fairly large AC motors. As this is a freezer, it does have cooling fans, compressor motors, etc. Once the output of this gate goes high, this wire goes high, and it's fed straight through to one of the inputs of this second gate. So one input of this will go high instantaneously. The other input is wired to this capacitor and these two resistors. So the high level on this line will slowly charge up this capacitor through these two resistances. And eventually, this voltage on this line will go high enough to turn on this guy and activate the other two gates. Okay, well that's well and good, but what is all this transistor stuff here? Well, think for a minute if this capacitor has charged all the way up, and then the switch closes, which causes this output to go low. When that output goes low, this transistor will turn on, because it's a PNP, pulling its base low turns it on, and it will throw a bunch of current into the base of this NPN transistor, which will in turn flash discharge that capacitor. So this is sort of an anti-glitch where when the door is closed after being open for less time than it takes to sound the alarm, the capacitor will be fast discharged, even if you close it just for half a second, and you'll have to wait the whole charge period of this timing capacitor before the alarm will go off again. So it's anti-annoyance, anti-glitch, trying to do the right thing in the circuit here. Now let's talk about these two gates down here. These two gates are both timing circuits. This timer, the timing capacitor, is charged by the 75K resistor and discharged by this 154K resistor. One of these is twice the other, so if there's 3 parts total, then you'll charge for 1/3 of the time and discharge for 2/3 of the time. As it happens, 10 microfarad, 75K, and 150K leads to a time of about 750 milliseconds and about 250 milliseconds. It is important to note that the way that the output of this gate is wired, when this is high, you are discharging through this NPN transistor and this resistor, and when you are low, the feedback goes back here to this PNP, and you charge the capacitor. So you charge when the output is low, and you discharge when the output is high. That's why the discharge time is longer. It has to go through a larger value resistance. Also, you might be scratching your head a little bit about, why didn't you just wire the input of this PNP to +5 instead of wiring it to the output of the first gate? You can only charge this capacitor through this transistor when the output of this guy is high and can supply current to the emitter, and the output of this gate is low and it can turn on the base of that transistor. This is a consistency thing. If that were not there and you just hooked this to 5 volts, then this capacitor would be charged all the time, instead of taking longer to charge up the first time that this goes high. I hope that explanation made sense. You'll see it in action in just a minute, and it'll probably become a little bit clearer. The output of this first stage also drives a MOSFET down here that drives an LED that actually turns on when the alarm is sounding. And we'll see that on the breadboard. This stage over here is the timing circuit for the beeper, because there's both a light and a beeper. Now this stage has the same 10 microfarad timing capacitor. However, it has a 20K discharge resistor, which means when the output of this gate is high and the buzzer is sounding, it won't take very long for this 10 microfarad to discharge through this 20K, and the beeper will sound for a much shorter time than the light is on. Also, when the output of this gate is low, this PNP transistor is on, and it is flash charging this 10 microfarad capacitor for the next cycle. There's also a little switch here. This is the beeper on-off switch. When you open that switch, this 4.7 meg pull down is keeping this input of the gate low. Consequently, this AND gate output will never be high because one of its input will always be low. You might think that you don't need this pull down. This is all a 74HC logic gate. HC logic gates have a nasty tendency for their inputs to float when nothing is connected. So this 4.7 meg pull down provides just enough pull towards ground to keep that input low when nothing else is connected. Looking at this circuit, I expect people are going to have a couple of objections right off the hop. The first objection they're going to have is, why did you create all these 555 timer-like circuits that use the charging and discharging of a capacitor and voltage thresholds to do timing? Why didn't you just use a 555? The answer is that I have 3 timing circuits here, 3 capacitors, and 3 different times that they are creating. So I would probably have to use perhaps a 556 to implement these 2, and then a separate 555 to implement this guy. And when possible, I like to try and get my hobby projects all on one integrated circuit. Now, I have heard of these mythical 558, which are 4 independent 555s in one package. However, although FutureLec does apparently imply that they have stock of them here, I have not found anybody that claims that they are making these 558s in regular production. As opposed to the 74HC7001, both in dip and surface mount, which is still an active production item. The other objection that I suspect people will have with this circuit is, geez, Salty, you've gone to so much trouble here when you could have just used a microcontroller. It might even be cheaper to use a microcontroller. What does a microcontroller cost in quantity 1K as opposed to this Schmidt trigger input and chip and all these passives and discretes out here? And I gotta say, I believe that you are absolutely right about that. If we look at the per unit cost at 1K quantity for this 74HC7001, it's essentially 91 cents. If we look at the per unit cost for a PIC 12C508, it's essentially $1.03. And the PIC allows us to get rid of all of this passive stuff around here because we're not using RC time constants to do timing. Now we're doing timing inside the microcontroller. And the microcontroller might even allow us to have some other kind of bell and whistle, like variable timing, perhaps, based on another switch you could throw. So yes, you're absolutely right, you could do this on a microcontroller, and it's probably better engineering if you did. However, code is my day job. When I do an electronics project for fun on the weekend, I want to be slinging transistors instead of writing lines of code. And that's why I didn't do this with a microcontroller, even though it probably would be better engineering. Alright, let's actually do a simulation here so you guys can actually see this in action. And what we're going to do first is just to sort of establish the steady state. Remember that when it comes to this switch, that's an open door, just like it looks. That's a closed door, just like it looks. So we're just going to have 100 milliseconds of the door being closed to let the circuit settle out to a steady state. Okay, I went over a little, 107 milliseconds, fine. This switch is allowing the 47K, 1K voltage divider to bring down the voltage at the Schmidt trigger buffer to 104 millivolts. Consequently, the output of this is low. That low output is turning on this PNP transistor, which in turn is turning on this NPN hard. And this capacitor is discharged. Both inputs to this AND gate are low. Its output is low. Nothing is really happening in the circuit. With the possible exception of the low output from this stage, turning on this transistor, flash charging this capacitor, so that the beeper is ready to fire at any nanosecond. Now we're going to open the door. And what's going to happen is this output is going to go high after a short delay. You can see the RC time constant right here. That's 106 milliseconds, and at about 120 milliseconds, it's fully charged. So it's about a 15 millisecond delay charging up this capacitor through the 47K. This stuff is no longer in the circuit because the switch is open. Because the output of this buffer has gone high, one input to this gate is already high. And this PNP transistor is turned off. It's no longer discharging this capacitor. What is happening is that current is slowly trickling through this 200K resistance and charging up this 10 microfarad capacitor. Eventually, that will cause this voltage to go high enough to exceed the high Schmitt threshold of this Schmitt trigger AND gate, and this output will turn on. Let's just run it until it does. In simulation, it's about 2.8 volts that turns on. On the real breadboard, it's a little bit higher. Now I want you to notice something about this third stage here. This capacitor is completely discharged. And the reason it's completely discharged is because there's really nothing to charge it up. This guy would like to charge it, but it can't because its power supply, its emitter, is connected to the output of this gate. I mentioned this before. What this ensures is that this capacitor stays discharged until the output of this gate goes high, and the door open delay has elapsed. Alright, the output of this guy went high, and now one input to this guy is high, and this capacitor begins to charge up through this PNP. This PNP is on because the output of this gate is low. Remember, the charging of this capacitor only happens when the output of this gate is low. And the charging time is shorter than the discharge time because 75K is smaller than 154K. So we're just going to run this until this guy charges up enough, watch that voltage right there, for the output of this guy to go high, which will turn on the light as well as something else. So this guy exceeded the input Schmitt trigger threshold of this AND gate. One of his inputs was already high because it was directly wired to the output of this gate. Now this is on. That has turned off this PNP transistor, so it's no longer charging. It has also turned on the light, and it's turned on this NPN transistor to slowly discharge that capacitor through the 154K. Another thing that happened when this output turned on is this AND gate instantaneously turned on the beeper because his timing capacitor was pre-charged by this PNP transistor, which happened while the output of this gate was low. Let's go ahead and run this until the beeper turns off. That will happen relatively quickly because a high-level output on this AND gate causes this NPN transistor to turn on and drains this timing capacitor through a 20K resistor. Beeper has turned off. You can see it down at the bottom here. So that was about 2.3 seconds. And this is about 2.52 seconds. So about 220 milliseconds. However, notice that the LED, the middle line here, is still on. And that's because although his output is high and his capacitor is being discharged, it's being discharged through this 154K resistor, which is taking longer. So we're just going to keep running this circuit until this capacitor discharges, which is going to take a while because it's going through a large resistance. So you can see the output of this gate has gone low. That has turned off the MOSFET and turned off the light. It's also turned on this PNP transistor, which has flash charged this capacitor all the way to 5 volts already. And, in addition, because the door is still open and the output of this gate is still high, we've also turned back on this charging transistor, that is now slowly charging up this 10 microfarad capacitor. So let's just watch this whole thing happen again. Light and buzzer turn on at the same time. Buzzer turns off relatively quickly, light stays on for a while, and then there's a dead time determined by how fast this PNP transistor can charge the capacitor through the 75K resistance here. Again, once this gate turns on its output, this gate turns on instantly. Both the light and the beeper start up at the same time. The beeper will turn off more quickly because it has a smaller time constant due to the smaller resistance. There you go. Beeper has turned off, LED is still on, and then the LED will run for approximately 700 milliseconds. There you go. Let's sit through one more cycle. As long as this is high, this guy will keep going high, low, high, low, high, low at a slow rate. And on the rising edge of this guy, the beeper will sound for a much shorter amount of time because of the faster discharge of this capacitor by this 20K resistor. There you go. Now, let's talk about an interesting case. Let's suppose the alarm is going off, the light is flashing, the beeper is beeping, and someone closes the door. Can you think through this circuit and think about what's going to happen when that door closes? Go ahead and pause the video and make a prediction, and then we'll actually run the simulation and we can see what happens. Okay, our LED and our beeper are both on. You can see they're both high here. Now we're going to close the door. So when that door gets closed, the current coming through this 47K capacitor is sunk into ground through this filter, and we'll also have to discharge that 100 nanofarad a little bit, but it won't take too long to discharge the 100 nanofarad through a 1K. Watch this voltage right here crash extremely fast. As you can see, that voltage went down quite quickly. Nothing like the smooth ramp up when we opened the door. And as a result, this hysteretic buffer here has gone low extremely quickly, which has turned on this transistor, which has turned on this transistor hard, and there was a flash discharge of this timing capacitor. Not that it really mattered how fast that capacitor discharged, because the output of our buffer is wired straight to this input of this AND gate. If either one of these inputs goes low, the whole AND gate snaps off instantaneously. Well, nanoseconds. But this capacitor also flash discharged down to about 18 millivolts very, very quickly. And you can see down here the light is off, the beeper is off, and you can see here, let's just run that just a little bit more, you can see down here, these guys also snapped off extremely quickly. So that's the circuit in simulation. Now let's actually go over to the breadboard, and I'll show it to you in action for real.
So just to show you the setup, we have our little light and beeper thing from Adafruit. I'll put a link to that in the description. There's our circuit on the breadboard, and we've got our meter framing, you fuck. We've got our meter over there watching the voltage on the main capacitor, the door open delay capacitor, and obviously that guy right there is our magnetic reed switch. And I'll cut you guys back in after I've zoomed in on the breadboard. I've got kind of a bizarre setup here for mounting my camera. It's a little weird. It's going to take me a second. So we've got a 12-volt wall wart over here. It's plugged in through this cord into the breadboard. And then the 12 volts goes into a 7805 right here, and that gives us our 5-volt rail. The circuit kind of wraps around the chip kind of in a clockwise direction. This little guy right here is not a resistor. He's actually our 1000 microhenry RF choke for our input filtering. And the rest of the circuitry just kind of loops around here. Let's go ahead and look at it in action, then you guys can see how it actually works. Lost my ground connection while I was messing around with stuff. So the reason the meter was flashing back and forth was because 18.6 millivolts is right on the edge of what the 20 volt range can kind of discriminate. And so it kind of goes back and forth between 0.1 and 0.2. It can't quite decide. You can see it's stable on both the 200 millivolt and 2 volt ranges, but we're going to be going above 2 volts, so we have to go on the 20 volt range, which isn't quite as accurate. So right now, the door is closed. You can see right here. So we can open it up. When it does, watch that wind up as the first stage flips over and starts charging that big capacitor. This is the big capacitor here. It's going to take this a bit to charge up. Unlike in the simulation where it flipped at 2.8, this isn't going to flip until just over 3. And of course, when you close the door again, it goes off right away, and the voltage goes right back to where you'd expect it. Now I can also show you what this thing sounds like with the beeper just going on for as long as the light does. I don't know if it'll come through how ear-piercing it is on camera. These two TO220s here are the MOSFETs, and so I can just take the one that's hooked up to the beeper and hook it up to the drain tab of the light. And then you'll be able to see, oops. God, I can't keep these things on the, so I don't know if it comes through on camera how freaking obnoxious that is and makes you want to tear that thing off the wall, throw it on the ground as hard as you can and stomp on it till it's in little pieces. But for whatever it's worth, that's why I went to the trouble of making a separate beeper timing circuit. Okay, I hope you've enjoyed that. I do think I probably am going to try and make a real circuit board for this, mostly with surface mount components. If nothing else, it's resume material. The other thing that I think would be awfully cool is, what if I could make that SMD circuit board small enough to fit in the bottom of this little thing and just have little Phoenix connectors coming out here for hooking up the reed switch? That'd be pretty cool, no? We'll see, maybe a future video. Anyway, I hope you've enjoyed this, and I hope that you are staying salty, my friends.